Okay, welcome to physics. Today we're going to talk about springs and spring energy. Okay, we did already talk about a little bit, but stuff I can't really show on the video yet, maybe next year. But when we talk about a spring, now in physics, we talk about an ideal or a perfect spring, which means as you stretch it, the increase in the force is linear with its displacement from equilibrium. So let's look at this. We got a spring here, and the springs in physics are kind of like the springs in your car. So you can compress them or you can stretch them. For the one I showed, it's just a stretchy spring. So this equilibrium point would be when there's nothing pushing on the spring or pulling on the spring. So there would be a force at equilibrium of the spring equal to 0. Because there's nothing on there. You can't push nothing or pull nothing. Newton's third law. Okay, so as we take and we apply a force to the spring in a downward situation, we can stretch it so we could say that, later the spring is stretched down to there. At that point, we have a force that the spring must be putting on, right? Because in order for me to stretch this with my little finger, I'm applying a force downward. Which way is the spring applying the force? Upward, right? Opposite of the way I'm stretching it. Now, if I push it in, it'd be the same thing. I'd be pushing up, the spring would be pushing down. So the thing with the spring, it always pushes the opposite way that it's stressed or taken from equilibrium. Okay, so this is what this Hooke's law states. Hooke's law states that the force of a spring is equal to negative kx. Now, like I said, this is kind of the quick version. I said that 3 days ago. Okay, so what do you think K stands for when we're talking about a spring? That is a spring constant, and that's a little k. It's a spring constant. And it's not a universal constant for all springs. It's a constant for a specific ideal spring. And the springs that we're going to do labs with here are actually really good. They have a constant. You can stretch them too far and ruin them, but for the forces that we're going to be applying, it's going to be very close to constant if you do your labs correct. So that's like a spring rating. How strong is your spring? This K tells you, well, it gives it a rating. So what do you think this X is? That X is a displacement. So if I stretch the spring this far, x1, versus stretch the spring this far, x2, which one's going to have a stronger force? x2, right? Because we know that when we pull strings, the further and further, they get harder and harder and harder, or compress them. So this is then displacement. So it's not distance, but it's displacement from equilibrium. So how far are you stretching this thing from equilibrium? And this is called Hooke's law then. The force of a spring is equal to negative kx. Now they put the negative in there a few years back, and what the negative idea is to remind the person looking at the formula is this. If I stretch a spring down this way, the force of the spring is going to be upward. Do you agree? The force is upward. The displacement, though, is downward. So this force is going to be in the opposite direction of the displacement. And that's why they put that in there. So the force of the spring is always going to be opposite of the way it's displaced. If I would push up on the spring, then the force of the spring would be in the downward direction. Okay, so I asked you earlier, do you think that a spring can do work? Right? You think a spring can do work was the question. I'm going to move our spring here a little bit. Okay, so you guys told me that, yeah, a spring can do work because it changes the energy. It makes things go faster. You release them like a dart or a school bus. So let's look at what happens. If I stretch this, a displacement, here my force would be 0. Here my force is a little bigger, little bigger, little bigger, and little bigger as I get further and further from equilibrium. And we said that this relationship is ideal or perfect for the things we're talking about. So what that means is we're going to have a linear relationship. It's going to be a constant change. So if this here is force, and this is displacement, right here would be at equilibrium. There would be 0 force at a 0 displacement. And we can see that in the formula. Force of the spring is negative kx. If the x is 0, the force is 0. Or you can just look at a spring and know that. Yeah, thanks for reminding me about that. The question was, what is a K labeled as? Well, if there's ever a time when you need to label or figure out a label of anything, you just solve for it and you look at the factor or the labels on the other side. So if you go K, you could say that it's force per displacement. A force is in newtons, and displacement is in meters. So that what that means is I'm going to increase my force for every meter that I stretch this. So it's like meters per second, but it's newtons per meter. Okay? Okay, thanks. So back to our understanding of how this force changes. Well, it's a linear, if it's an ideal spring, it's a linear increase, a linear relationship. And we know that work, we said work of anything, including a spring, is force that's parallel to a displacement. Right? We talked about that yesterday. Okay, so if we look at the force of a spring, if I do end up stretching this thing to this point, and I look at Hooke's law, the force of the spring at this point is kx. I'm going to drop the negative for now because we're talking work and energies, and it doesn't have that direction. The energies don't anymore. So the force at this point would be kx. Do you agree? And the x would be defined as this distance from here to here. If we look on our graph, this x here is going to give us a force out to here, right? So that's the force that our spring applies at this displacement. But if I release it, so let's say, I've got a dart on here, and I've put the dart in, and I've stretched the spring down to there. When I pull the trigger, that spring is going to move back to equilibrium. Do you agree? So how does the force change as it moves back to equilibrium? It gets less and less and less linearly. I don't know if that's a word. Okay, so the work of a spring can also be determined by the average force, because we know this is a changing force, right? And so the better representation would be the average force over a distance. Right? So how would we describe this average force as the spring gets unsprung or sprung, however you say it? How would you describe that change? Okay, so we didn't quite get there. But if you look at this, where would the average force be on the graph? Right in the middle, right? Right here it would be, because for every piece below, I have the same incremental change or difference above. Right? So down here, up here. Okay, so any ideas now? Well, let's just say that right up here, this is my maximum force of the spring. So that's my highest number. Down here is my minimum force of the spring, which is 0, right? So when you want to take an average of two numbers along, like something like a number line that's linear, how do you do it? Add them together and divide by 2. That's exactly right. That is the average force in this situation because it's an ideal spring. Does that make sense? Okay, so if you look at this, the work that a spring can do is then an average force. So we could say that kx at the max divided by 2, right? Because down here it's 0. So we just take the max force, divide that by 2. That's what the force is, right? So now we got to figure out what is the displacement over which this average force is applied. Very good. Very good. Okay. So, yes, the work that the average, or the force is going to occur over this same displacement as the maximum force was achieved, right? Because once it gets back to equilibrium, then the spring is going to start working on itself, slowing it down, and whatever is picking up that energy is going to be, leaving the spring. So that displacement then is the same. The displacement of the work is the same displacement that we stretched the spring in the first place. So then the work of the spring becomes 1/2 kx squared. And we can also call that the potential energy of a spring. So the work of a spring is 1/2 kx squared. Here's the potential energy of a spring formula for you right underneath the Hooke's law. And then we can take all the potential in the spring and we can put it into the object that is being worked upon by the spring. Now you might say, well, how does that work? Potential and work, how does that all work together? Well, if you think of yesterday what happened, we said we have a potential up here equal to mgh, and that's due to gravity or the Earth, right? The Earth is going to force on this ball, and it's going to force over a distance, and then the ball is going to change its energy to kinetic. So there must be work done because the Earth is changing this potential energy into kinetic. So it's changing its energy. So how does this force distance thing flash out here? Well, work is force times distance. The force on the ball is equal to mass times acceleration, or in this case, mass times little g. That's the force on the ball, mg. And the displacement over which that force is applied to the ball is h. So that's how this whole potential energy of the Earth fits into this work idea. So really the underlying idea of all this energy is it's all the same thing. It's just tracking it or seeing how it's changing, seeing how it's going back and forth from kinetic to potential, or, quote, lost, unquote, due to increased kinetic energy of small particles, which we call heat. Okay. So that's kind of just the basics of the Hooke's law and the spring potential. There's one other piece that you have to become acquainted with before the semester test, and that's the idea of power. Oops. Power. Okay, so it's kind of an industrial revolution when they discovered the horse collar. So that was kind of an industrial revolution that's not in the textbooks, is the horse collar, because the horse would do the same amount of work as the oxen, but they'd get it done faster, so it was more powerful. Okay, so power is measured in watts, which is a big W, which is confusing because work is a big W too. One's a label though for the units. This watt is a unit label. And the definition of power is work per time. So how fast you can get the work done. Okay? So if you look at work per time, you would say work is force times the parallel distance. Do you agree? And how fast you can get that done in is what determines how powerful you are. But if you look at this, there's actually one more power formula. If you look at this, what is d over t? Velocity, right? If it's displacement per time. So we can kind of look at this power formula as applying a force parallel to a velocity or an average velocity. So power is either force times parallel velocity or just work per time, both measured in watts. Okay, hopefully this helps you with the understanding of the equations. We'll do some more examples and stuff with these things after the semester break.